So in an internal presentation in 1979, an employee of IBM made a profound and frankly prescient case against the use of AI. In a slide that went around the internet last year, they wrote, quote, "A computer can never be held accountable. Therefore, a computer must never make a management decision." Well, we've innovated since then and discovered that actually, they were wrong. A computer can be tortured. I'm here today to tell you how. But first, hey y'all, I'm Michael. I build and hack iPhone apps just like everyone else here. I've been doing that professionally for the last 6 years, though I've been shipping apps for, I think, getting close to like 15 now. In my spare time, I like to watch hockey and travel. In fact, I grew up in Nashville, but I recently moved here to the Netherlands. Lots of colleagues have read my code before and said that I belong in The Hague, so I figured I'd come see what all the hype's about. And it turns out they're right. It's a pretty nice place. At the same time, I've recently gone independent, so I'm available for contracting. You can find me most places across the internet at mhewlettdev. Now, this week, you're going to hear a lot of very talented speakers say lots of things about how wonderful and expressive the Swift language is. They're not wrong either. Its pivot towards safety away from the wild west of Objective-C allowed us to take our craft to the next level. And from it, we got brand new, albeit natural constructs like SwiftUI and async await that generally fulfill the core team's goal of creating a language that's approachable but powerful, and always modern, safe, and a joy to write. I'll let all the other presenters to grace the stage to tell you about that, though. Because, friends, that is not this talk. This talk is for while we're building these abstractions, when we push our code a little too far, and we get pricked by the thorns at the edge of the walled garden. This talk is, while in service of making life easier for our users, colleagues, and our future selves, we're forced to reconcile with the low-level truth of the problems we're actually solving, and the tools that we're used to start to prove inadequate. Just about everything I'm going to show you today is a bad idea, and reaching for them is often indicative of deeper problems in your architecture. You may have come to do iOS, but for the next 45 minutes, this is don't iOS. This talk is for when you promised your boss you'd have a PR up by the end of the day, and now you can see the sunrise out your window. So today, I hope to give you tools you can use when you need to mend the conceptual shear that develops between beautiful abstraction and grotesque reality. However, you need to be careful in using these. Everything I'm going to tell you about is experimental, unstable, and/or meant only for use in the Swift repository and standard library, though you can use it in all of your own projects. This is the deep magic. We can only gain wisdom through suffering, and today I intend to make you very wise. Please use discretion and don't hurt yourself or your users with it. Nothing lives forever except for temporary hacks. Now, for those like me that need a detailed list of what to expect in order to hold my attention, I'm going to start off with an inexplicably deep dive on modules, followed by a shallower wade into the pool of protocols, ending with a tangent on method dispatch and optimization. So let's get going. In Swift, all our code is organized into modules. They keep our code separate and independent, and therefore more reusable, testable, and maintainable. Our apps are modules in themselves, but modules are most obvious to us when we're using things like packages and frameworks. We can access the code in other modules via the import statement. This tells the linker to go grab all the code in the other module and make it available to us in our current file and our current module. There are a few commands we can give the compiler and linker to modify how to do that. You're probably already familiar with at least a couple of them. For example, there's @preconcurrency, which tells the compiler to stop yelling at you about sendable and all that. And @testable, which tells it to make any internal symbols available as if they were public, so you have more hooks for unit tests. You can actually go a little bit further than @testable goes, too. Turns out, you can fully disable access control altogether. That's what @private does. Now, there are two major downsides to using this. First of all, you have to specify it file by file with the source file parameter. You have to know which file the private symbols you want live in the other module. And if you want private access to multiple files, you got to specify this attribute multiple times. Also, that also makes it somewhat fragile if any of these file names ever change. Second, the module you're importing has to be compiled with the front-end enable private imports flag. Considering Swift Package Manager generally distributes packages as source, though, that's certainly feasible. God may judge you, but his sins outnumber your own. There's a couple more than just those, too. To introduce the other ones, I need to talk about umbrella frameworks. An umbrella framework is what happens when a framework depends on other frameworks, but also makes the symbol of those frameworks available to whoever imports itself. Apple does this a lot. For example, things like Foundation and SwiftUI are umbrella frameworks. When you import Foundation, you get access to all the symbols in its myriad of dependencies, like Core Foundation and Darwin. And likewise, SwiftUI even depends on Foundation and makes it available in the current scope when you import SwiftUI. However, Apple strongly recommends that you don't do this yourself. To illustrate why, let's say that we've made a cool new library to talk to our backend API that depends on AlamoFire. AlamoFire is great. Surely our users will want to use that for their networking stack too, right? Well, let's say that they've been around for a while, and they already have. In fact, they're on an older version of it and can't update all that easily. But now we've exported it, so there's a collision. Our version of AF and everything else conflicts with their version of AF and everything else. And the end result is a linker failure that prevents them from using our library at all. Swift typically tries to protect us from this with SPM. It's capable of managing these versions and even letting them live side by side while keeping them all separate. So we can depend on our version, and our users can depend on theirs. But I'm not your real dad, though, so I'm sure you know good and well what's best for your own project. So if we really wanted to create an umbrella framework, Swift lets us. That's what the @exported keyword is for. It's a modifier for the import keyword, just like the others I've mentioned so far. All that @exported does is take all the symbols in the module you import and make them available to anyone who imports your module. It even imports them into your module scope so that any symbols that are defined in the submodule look like they're coming from yours. In other words, it turns your package into an umbrella. Sometimes this is useful in refactors. When you want to break up one big package into lots of smaller packages, when we're the author of all the subpackages in the module that's importing them, we can use @exported like this in the parent package to prevent the need for us to go through every usage of the original package and also import all the new ones. Especially in a really big project, that can be very tedious. Now, the logical opposite of the @exported attribute, of course, is @implementation only. Typically, Swift lets you use imported modules in your public API, and those will automatically get re-exported and available in the scope of your users, but only the symbols you use in your public API and no others. However, this is kind of impure because it implicitly turns your module into an umbrella, albeit one with holes. @implementation only will patch those by guaranteeing that you can't expose public API from a module you imported in your public API or ABI. If you try to, you'll get an error. This helps us keep a very strict separation between our modules so we don't leak any API or ABI, which helps to make it easier to change the implementation details and move things around in the future. That said, I should mention that this particular attribute was obsoleted by SE 409 in Swift 6, in which you can attach an access control level to a module import. For the history of Swift until now, imports have been public by default, and they still are, which means that an import in one module can expose symbols to its client modules. However, now in Swift 6, you can also mark imports with any access control level. So marking an import with the package level or lower will cause it to guarantee you aren't exposing imported API to clients of your module. In the future, the default will switch from public to internal, meaning that imported symbols can only be referenced in definitions internal to the current module and not outside it, even within the same package, just like what the @implementation only attribute does. If you're on the Swift team and listening to this, first of all, please don't hurt me, but also consider putting this in the documentation for @implementation only, because it was really confusing to find out now. With all that said, there's actually a whole other system of module access control in Swift. If you think back to the Objective-C days, we used to be able to define extra functionality in our classes through what was called a category. It worked kind of like how Swift extensions do now, but the convention was that you would define them in their own header implementation pair so you could import them selectively and decide which extra bits and pieces you wanted your classes to have. The idea was that sometimes you needed access to extra things to make the functionality of the module or framework you're building function well, but didn't need to expose all that potentially dangerous complexity where it doesn't need to be. Swift has something kind of like that too. It's called the System Programming Interface, or SPI for short. The core team made it 4 years ago in the hopes that it would eventually replace @testable. It gives you tight control over which features should be available to exactly which consumers of your library, because you mark and label them all yourself individually with the @SPI attribute and give it a label. The label can be anything you want. Just tell the intended user of your library what it is, and they'll add the @SPI attribute with the same label to their imports of your module. For example, let's talk about the use cases the core team was imagining when they were building this feature. Perhaps we're working on our employer's SDK, which we both use internally and distribute externally. There's a handful of features that we sorry, I got lost. There's a handful of features that we want our app to support that we don't want the public to get their hands on, though. For those, we can mark those as SPI with a special label we decide on here. Then, over in the app, when we need to use those declarations, we can import our framework with the @SPI attribute with that same label we defined, and then those features are available in our app. We also definitely want to test it, but making all internal declarations open is a pretty broad brush to paint with. Instead, we can mark just the definitions that we want to test as SPI, and then over in the test module, we can import the SDK module with the @SPI attribute and the testing namespace we defined. We can even use that other label we defined for internal use too, and then those are available to test as well. That way, all the symbols that need testing are available to the tests, and we don't have to deal with the implications of breaking the usual access control system. However, you need to take care in protecting knowledge of the existence of these symbols, because anyone who knows the labels can import them too. Back in the Objective-C days, the way you'd manage this is by declaring them all in a private header that you'd pass around to those who need it and strip out of the release builds for everyone else. Swift actually has a similar kind of system too, through a Swift interface file. It's actually a lot like a header. It's nearly valid Swift with lots of weird attributes I'm talking about today. A watered-down version of it is what comes up when you jump to definition on a symbol in a framework where you don't have access to the full source code. When you import a module, the linker looks at this file to ascertain what's available in the binary. However, when we start using SPI, the compiler generates a second private Swift interface file alongside the public one. This file contains not just the public API that we want to expose, but also all of the SPI too, with all of the labels. Therefore, anyone who has that private Swift interface file can casually read through all the parts that you don't want them to see and use them anyway. Therefore, if you use SPI, you need to be sure to manually remove that private Swift interface file before handing out the framework externally. In service of protecting your SPI, you might also want to keep clients of your module from knowing that you rely on another module. Perhaps you only need to rely on it in SPI and don't want external API clients to need to deal with it. Swift has you covered there too, by marking your import as @SPI only. Doing this effectively makes the whole module you use part of your SPI. The type checker will throw an error if you ever do something that would cause something within it to be exposed to your API. Users of your API will never know it's there, but users of your SPI will get whatever use you need out of it for free, just from importing your module, without any extra attributes or labels beyond the ones they normally use to ask for your SPI. Note, however, that you have to pass the experimental SPI-only imports flag to make this work. There's one other way to create this sort of global SPI where you don't need a particular label, and that's with @SPI available. All you have to do is tell Swift the minimum version of the platform this SPI runs on, and anybody who has the private Swift interface for your module will have it available in that platform version and up. It's designed to work just like the regular @available. You can even combine them to tell Swift that a particular public API symbol is public API on some versions of some platforms, but completely unavailable to the public on others, while still making it available for internal use on more versions of those very same platforms. In this sample, this symbol is available as SPI on iOS 16, but doesn't become available to the public until iOS 18. And on macOS, it's available as SPI on macOS 13 and up, even though it's completely unavailable to the public API on any version of macOS. Be very careful when you use this, though, because it's the leakiest way to define SPI. Declarations marked with SPI available are the only type of SPI that always appear in the public Swift interface as well. They're simply marked as unavailable for every platform that the @SPI available declaration mentions. You have to manually remove these from your public Swift interface if you want to completely hide this from anyone who doesn't know how to use a disassembler. In some cases, that might not even be practical depending on your availability matrix. Let's think about this from the perspective of the overzealous library consumer instead of the author, however. every framework we use has one of these Swift interface files. And nearly all of them will specify per platform availability for many of their symbols. Many of those will be unavailable, and especially in those made by Apple, quite a lot of those actually do exist in more places than they claim to. Truly, if you wish to gather your ambition and lay it upon the altar of your own hubris, there's nothing stopping you from simply changing the availability in these interfaces yourself on your disk and go fishing for what works. Just please remember that the closer you stand to the light, the taller your shadow becomes. While the worst that may happen on your system is a crash, the nature of software is change. So what works for you now won't work forever, and it certainly won't work for your users forever. And that's all assuming you can get past app review. Absolutely do not ship whatever you find. Now, let's talk about protocols for a bit. They play a major role in our lives as Swift engineers, to the point that Apple even refers to Swift as a protocol-oriented language. They come in handy in lots of cases, like when we want to define a list of requirements that we'd like to depend on, compositionally add default functionality to related types, or constrain the list of types available in specific contexts, without having to worry about the actual underlying concrete type we're dealing with. They're even a critical tool for merely signaling intent throughout your codebase. It's a somewhat common pattern to define an empty protocol that you then make types conform to in order to document that they should participate in some kind of function, even if that doesn't imply adding additional functionality to the type itself. This is really common if you've ever used sorcery, and it might still come in handy if you're defining a macro nowadays. There's actually one really famous example of this in the standard library, which everyone here has likely become intimately familiar with over the past few years: Sendable. This type of protocol is called a marker protocol. Marker protocols are simply empty protocols with no requirements. It's very common to implement one by just defining an empty protocol and calling it a day. That's fine, but Swift allows us to go one step further and signal to the compiler that our protocol is a marker protocol with the @marker attribute. Adding this tells Swift that this protocol only has meaning at compile time and should not have any runtime representation. This means we can still do things like document it or use it as a generic constraint. However, if we ever try to do things with it that require the runtime, like using it as an existential or checking a type for conformance to it, we get an error. It simply doesn't exist in your binary. Most protocols actually do have requirements, though, and most types we implement conform to at least one of them, even if we often don't even have to write those conformances ourselves. In rare cases, this can lead to collisions. Let's say we work for one of those big companies with lots of disjointed teams with competing priorities. We have two different analytics services, and perhaps we're in the middle of a transition or something. Lots of analytics SDKs define a protocol requirement like analytics name for screens. So we have a data analyst readable name for each screen on our app reflected in their dashboard. We suddenly have a reason to reuse one of those screens another team made in our part of the app. But over in our corner, the context is different. So it needs another analytics name for our own analytics system. Suddenly, we can't have it both ways. The same property can no longer suffice to serve the same requirement from different protocols. To mitigate this, we could do something reasonable, like try to extract out as much as possible that we want to reuse from the screen and write a context-specific wrapper that conforms to the respective protocols for use in their respective places. But that would require reviews and approval from the other team, and the product manager is darkening our doorstep for stand-up in 15 minutes. It's time for a reasonable person to do an unreasonable thing. Fortunately, Swift has an escape hatch for us with the @implements attribute. Using it, we can define our own separate symbol and tell Swift that we want it to fulfill the completely unrelated analytics name requirement of our analytics library screen protocol. Now our requirements no longer collide with the other teams, and our data people would never know the difference. We even have a minute to refill our coffee before stand-up. Now, let's imagine we own every little bit of this mess. Perhaps we've defined a protocol for our analytics service, which is functionally identical to the other one, which also has a protocol. Rather than just use one protocol for both, we have hope that we'll eventually settle on one, so we'll just inherit ours from theirs in the meantime. We want to emphasize, though, that we want to use a different analytics name for our services, so we'll restate the requirement for it in our protocol. Crucially, though, this also gives the types that conform to our protocols a hook to define separate implementations for these overlapping requirements with the @implements attribute we talked about before. Usually, that's all this does, but we'll turn on the warn implicit overrides flag which will highlight to us when we've restated a requirement of a protocol. This is a hint that actually we need another annotation here. We could add override to the restatement, which is itself an undocumented feature of Swift to work around some early ABI weirdness, but that simply signals that this is purely a restatement, and that's not the case. Instead, we want to signal that the semantics are actually different here, and our consumer should provide two separate implementations. The situation I've described is a monument to all of your sins, towering above you like a fire-breathing dragon, ready to steal many of your nights and weekends to come, but should you find yourself in this situation, you can do that by marking your restatement with the attribute @non-override. Now the warning goes away, and we know about the semantic difference between the two variants when conforming to these protocols. One of the core features of protocols in Swift is that you can use them as existential types instead of merely as generic constraints. When this happens, you get a kind of box for free, where Swift passes around arbitrary data that conforms to the protocol without you needing to know exactly what data type that is when you use it. This is what's happening when you use a protocol as a type, which you can do using the any keyword nowadays, or just bare like any other type. However, you can only do this for protocols that don't have requirements for associated types or capital S self. If you want to pass one of those around, you need a concrete type that conforms to the protocol. We often call these type erasers. You're already familiar with several of them, like any view, any hashable, any collection, those. Defining one of these depends on the protocol you're wrapping and isn't always easy, and the traditional way of doing it doesn't necessarily make it obvious that one exists at all. But Swift actually has a built-in mechanism for helping us guarantee our implementations are matching the API contract of a true type eraser and associating them with the protocol they're erasing. You can do so by adding the @typeEraser attribute to the protocol that's getting erased and passing it the concrete type that acts as an eraser. Adding this does a few things. First of all, it adds a few requirements to the eraser type. Now it has to actually be a concrete nominal type like a struct. It has to have the same or more open access level as the protocol it's erasing. It has to conform to that protocol. And it has to have a generic initializer that takes any value conforming to the protocol it erases. Second, doing so opts you into a hidden feature of the Swift compiler, automatic runtime type erasure. You see, some protocols have requirements for opaque types. If you're not familiar with opaque types, it's basically the sum keyword, as in SwiftUI's view requirement of body having the type of some view. Lots of us mentally conceptualize opaque types basically like existentials, but they're not the same. An existential type has a concrete representation at runtime that can wrap any other type that conforms to it, but opaque types are mere generic constraints that only exist at compile time. For them to have a similar runtime representation, you need to make a type eraser for it. Adding the @typeEraser attribute to a protocol also tells the compiler that if the protocol has any requirements for opaque types, it should implicitly wrap the implementation of that requirement in its type eraser before returning it. That means that even view's body in SwiftUI, which officially returns some view, is technically functionally identical at runtime to as if it was statically defined to always return any view. Normally, if the underlying value were to be changed or modified at runtime, it would have to exactly match the original type, but this allows the underlying type to change or be modified while still allowing us to think about it as a standard existential when we're writing the code. This is one of two features that exist to support SwiftUI previews. It's only half the picture, though. There's one more important puzzle piece here, and it's a wild one. You'll notice that when you make changes to your view code, the preview typically updates real fast. It's a full-fledged instance of the iOS simulator, but that takes a long time to boot. It's clearly not fully rebooting the simulator for every change, or even the app that's running on it. This kind of hot reload is really common with cross-platform frameworks built with far more dynamic languages like React Native and Flutter. That said, Objective-C is technically capable of achieving a similar level of runtime dynamism. You should never ship one of these in Objective-C either, but it was fairly commonly known as swizzling. In Objective-C, rather than calling functions on types, you would send a message to a class using a selector, which would then look up what method you're referencing, find its underlying implementation, and call it. You could implement a swizzle in Objective-C by getting a different method on that class and going through its whole song and dance to grab the right bits of it, and then tell it to exchange the implementations between that method and the method you want to swizzle. So calls to the method you chose would actually redirect to the method you're swizzling, and vice versa. Don't forget to call out to Grand Central Dispatch to make sure this can only happen once, too, or things could get really weird. It was commonly used to patch in functionality of frameworks you don't own and poke around at bits you're not supposed to touch. It's really fragile and confusing, and given Swift's whole focus on safety, it obviously doesn't support it outside the overlay on the Objective-C runtime. Except that it actually does. It's even safer than the way Objective-C does it, too. All you have to do is create a new declaration that you want to swap for the old one, and then just add the @dynamic replacement for attribute to it, specifying the declaration it should replace. There are a couple key differences from Objective-C, though. First of all, Swift requires that the method signature of the replacement matches the signature of the method being replaced. It must take the same parameters, return the same type, be defined on the same type, even if in an extension, have the same concurrency context, etc. This differs greatly from Objective-C, where you could just sort of do anything to anything and break any compile time assertions if you wanted to. Second, the calling convention for the original implementation is much cleaner. In Objective-C, the way you'd call the original method you're overriding from the one you're swizzling in would be to call the method that you're injecting. This is super confusing, and if you're just reading the code at the definition site, especially if you don't have the context of it being the target of a swizzle, any hint that the method don't have the context of being target of a swizzle because it looks like you're just recursing. You don't get any hint that the method that runs there isn't going to be the one you're referring to, or which one it will actually be. In Swift, to call the original implementation, you just call the original function. You don't need to think too hard about it, and it just does what the code says it does when you read it. Third, you can't provide multiple dynamic replacements for the same method. Veterans of the Objective-C and maybe even jailbreaking days will know the chaos that could ensue if you tried to swizzle the same method multiple times. It would suddenly become completely unclear exactly what would happen when you called just about any function, and nearly all assumptions would break down. Abandon hope, all ye who enter here, because that way lies madness. In the world of jailbreaking, entire tools like Mobile Substrate and Theos were developed to deal with this problem specifically. Swift solves it by simply disallowing you from doing it more than once. However, I should note that when I was testing this assertion in Xcode for this talk, I found a number of cases where this didn't appear to be true. So while you shouldn't be using this anyway, lest your naive insolence crush you like a bug, you should be extra careful relying on this assumption, and file radars if you can break it. All this said, the only methods that can be dynamically dispatched the only methods that can be dynamically replaced are those that are dynamically dispatched. To explain that for those that don't know how the internals of the runtime works, most functions in Swift are statically dispatched. This means that the location in memory of the function that gets called is well known at compile time. Functions in the global scope, functions defined on value types like structs or enums, or functions defined on final classes are all examples of functions that would typically be statically dispatched. The corollary of this is dynamic dispatch, in which the location in memory of a function that runs is looked up at runtime. Examples of these are methods defined on non-final classes, which are most methods defined on classes, or functions that exist to conform to a protocol. Each instance of a class carries around with it what's called a virtual table, or vtable, which is essentially just an array of functions. When you call a method on that class, it just grabs the first function out of that array and calls it. If that function calls super, it goes one index over to where its parent class's implementation lives and runs that, and so on. Likewise, if a type conforms to a protocol, it carries around what's called a witness table. A witness table for a protocol basically just keeps track of where all the implementations of a protocol are for a particular type, whether they be on the type themselves or in an extension of the protocol. Dynamic replacement typically works by simply replacing the appropriate function in a type's vtable or witness table. Turns out that in Swift, though, you can actually force a method to be dynamically dispatched, even if it would normally be statically dispatched. All you have to do is mark it with the dynamic keyword. When you do that, it doesn't necessarily participate in traditional dynamic dispatch through the Objective-C runtime, virtual dispatch, or witness dispatch, but it guarantees at least a logical branch to see if there are any replacements necessary for it. If there are, it calls the dynamically replaced version instead of the original implementation, and shout out to Harlan Haskins for helping me walk through the implementation details here. All that said, if you pass the flag front-end enable implicit dynamic to the compiler when compiling a module, everything that can be dynamic within automatically will be, so you don't necessarily need to specify it yourself on each declaration, But just know that it can't work for anything that can't be dynamically dispatched, and more on that later. Put all that together, and that's how Xcode previews work. Xcode loads up a simulator, installs a little app on it to display your specific preview, infers your preview be dynamically dispatched, wraps all its contents in any view, thanks to its annotation as a type eraser, marks it as a dynamic replacement for the function that decides what gets displayed in the preview window, compiles your app as a dynamic library, and then loads it in the preview. It is unmistakable madness, but through madness comes the beauty of function, usually at least. I mentioned before that this doesn't work with anything that can't be dynamically dispatched, but also that nearly everything now can be. The operative word there is nearly. There are a handful of situations where you can't, or at least shouldn't. The situations where you can't are the somewhat obvious ones, whole types, deinitializers, enum cases, etc. But the ones where you shouldn't are often a bit more of a judgment call. For judgment calls, you should really leave that up to the Swift compiler. Frankly, if you haven't tuned me out yet, it has better judgment than you do. However, if you really think there's absolutely no case where something should be dynamically dispatched, you should consider if this is a case where you should be inlining it. All the code we write eventually gets compiled down into machine code, which can often be structured wildly different from our source code. It can apply lots of different optimizations to make our code faster and or smaller, like getting rid of functions that don't get called or pasting the definition of a function into all the places it's used to save the overhead of a function dispatch. That last bit is called inlining, and the compiler will decide on its own to do it for lots of functions that get used often, but there are some very specific times when you might want to force it to do so. When you do, you can mark that function as inline always. That is great for speed, but I personally use this somewhat often in security-sensitive contexts. For example, until recently, it was impossible to use a library to access the keychain without defeating half the purpose of the keychain API. This is actually the only trick I'm going to show you today that I recommend using in a production context, because accessing sensitive data and functions that aren't inlined leaves a trivial hook for an attacker to inspect your binary and find your secrets, or potentially even swap out the implementation of your sensitive function for their own with either a cracked version of your app or even at runtime in some cases. Deviation from the norm will generally be punished unless it's exploitable, but this actually prevents an exploit. Such an attack is number 7 on the Open Web Application Security Project's list of the top 10 most common vulnerabilities in mobile apps. All the keychain libraries out there inevitably introduce some kind of dynamism that introduces a vulnerability like this, like using a reference type or a protocol. And even the ones that don't fundamentally can't inline their methods into your binary for the most protection possible. Marking a function as inline always will let it exist like a normal function in debug builds, but it'll force it to be inlined if it can be in all release builds. So if you want to open up Hopper or IDA to verify what I'm telling you and see the disassembly for yourself, don't freak out if you see it in the binary in a debug build, and try it with an archive instead. If it's still there, check to make sure the function isn't recursive and that you haven't marked it as dynamic. Because the one caveat here is that inline always silently loses the precedence war with any conditions that are incompatible with it. While we're on the topic of method dispatch shenanigans and optimization, I'm going to talk briefly about one public keyword that I wish you all knew less about: final. The final keyword ends the inheritance chain of a class, specifying that no other classes can inherit it from the one it's applied to. This does help the optimizer make more detailed assumptions and allows it to act more aggressively when compiling the file it's defined in. Sure. But I get the sense that the common usage of it somewhat overblows that effect. In my past 3 years as a consultant, I've seen teams both huge and tiny abuse this keyword to generally marginal results, often while shooting themselves in the foot later on. Final is not merely a performance tool, as it fundamentally changes your API. When you apply it, it cuts you and your teammates off from helpful hooks for things like testing and extension. I see this regularly coming back to haunt teams where someone wants to override some functionality in some context, but they can't because the base class is in a module that they don't own, and then removing the keyword requires often weeks of coordination and analysis and review and such when it was added thoughtlessly in the first place. This compounds if you're working on an open source library you plan on distributing, because then it affects not just your teammates, but the broader community, who then has the maintenance burden of opening issues and PRs, or even forking it to fix it themselves, and all of y'all get to deal with the extra maintenance burden over time. To make matters worse, the hypothetical performance gains that it was added for are likely not real anymore either. with whole module optimization, Swift infers this keyword for you by analyzing usage of these classes across your module and automatically pruning the need for dynamism on all the leaves of the tree. This has been on by default in release mode since Swift 3, and since Swift 5.8, which was released March of last year, cross-module optimization has been on by default. So the compiler can now infer this for your entire app, including within all your dependencies that you have the source code for, which is nearly any Swift package manager dependency. As a result, you should only be adding final to your declarations in a small handful of scenarios. The ones that I found so far where it can be useful are when there's some kind of negative impact to something like security or stability if someone else overrode your declaration, if you anticipate a significant maintenance burden over time from someone else overriding your declaration, or if you've tested it yourself and found a concrete significant performance boost in this specific case for making it final. Be sure to use the profiler before you assume that. Finally, if you'd like to test any of the optimizations I've mentioned today, you can do so by changing the Swift optimization level setting in your build configuration in Xcode, or by passing the appropriate flag to Swift-C at the command line. Options are none, size, and speed. All of those options are painting with a pretty broad brush, though, since they apply to your whole program instead of just the part you care about. Swift actually lets you apply these to individual declarations, too, with the @optimize attribute. It takes the same options that the build setting does, but applies to only the things you mark it with. That way, you can investigate the performance implications of adding or removing optimization to specific functions, or do some binary inspection to see what survives the optimizer and what doesn't. It'll override the setting that you or Xcode pass to the compiler, too. So if you want to do something like keep extra debug information for a method you suspect might be buggy but would normally get optimized away, you can mark it as optimize none and ship it in the next version to hopefully improve the quality of your production bug and crash reports. Now, that's all I got. I truly hope this was the least useful talk you'll hear this week, but if you find yourself burdened with the necessity of to reach for something I showed you, well, may you never suffer from insanity, but enjoy every minute of it. Now, don't forget, you can find me on the internet via my website, hewlett.tech, at hewlett.tech on Blue Sky, at mhewlettdev on Twitter, or at hackaderm.io at i.io to that for the Fediverse. And remember that I'm available for contracting starting sometime next month, maybe January. So if you'd like to help with your help with your Apple platform app, send me an email, and I promise I won't do anything I showed you today to your code base. Thanks, Al.